Thank you for the introduction. I will talk about the hydrogen visualization techniques to analyze hydrogen diffusion in polycrystalline materials. So to elucidate hydrogen mechanism, it is important to understand how hydrogen diffuses in the metals. So far, there have been various hydrogen visualization techniques such as escape effect. And the conventional techniques can visualize the hydrogen distribution with high spatial resolution, but the observation area is often restricted. In addition, the spatial and the time resolution depend on the scanning rate of probes or electron beams. Therefore, we often face the difficulty of visualizing the hydrogen distribution of a large view with high spatial and time resolutions. So we developed another approach. We introduced hydrogen atoms electrochemically into the spacemen, and they diffuse to the other side. On the other side of the spacemen, a polyaniline layer is polymerized. In the previous research, we reported that the polyaniline changes its color due to the reaction with atomic state hydrogen in metals. Because the visible color change is caused by hydrogen in metals, the hydrogen distribution can be observed in an optical microscope, which can observe a large observation area with high spatial and time resolutions. So far, the spatial resolution of the polyaniline has not been investigated. So in this research, we attempted to visualize microstructure-dependent hydrogen diffusion in polycrystalline metals. So the objective of this research is to develop a microscopic observation technique for hydrogen diffusion in metals. So pure nickel film was used as a specimen. The specimen was annealed and electrically polished in the solution. The final thickness of the specimen was 0.11 millimeter. On one side of the specimen, the polyaniline layer was polymerized, electrically polymerized in this solution. The specimen was polarized at a constant voltage of 1 volt for 150 seconds. This same image shows the cross-sectional view of the specimen. On the nickel film, a thin and homogeneous polyaniline layer was polymerized. So if the morphology of the polyaniline layer depends on the microstructure of a pure polycrystalline nickel, the color change of the polyaniline may be caused by the morphological distribution. So we check the crystal structure and the thickness of the polyaniline using TEM observation shown here. Like the thickness of the polyaniline and the crystal structure of the polyaniline layer showed no dependence on the microstructure of the nickel. So using this polyaniline layer, we visualize the microscopic hydrogen distribution. This is a schematic of the process. One side of the specimen was immersed in electrolyte, and the hydrogen was electrochemically introduced into the space. On the other side of the specimen, polyaniline layer was polymerized, and the color of the polyaniline was observed using the embodied optical microscope. If the hydrogen atoms enter the specimen, they diffuse to the other side. Because the color of the polyaniline changes by the reaction with hydrogen atoms in metals, based on the color distribution of the polyaniline, we can visualize the hydrogen flux distribution in chemical. During the hydrogen visualization test, hydrogen charging was conducted in the 0.1 sodium hydroxide under these conditions. So this is optical image of the polyaniline before hydrogen charging. So before the test, the color of the polyaniline is purple. This is a scratch, the artificially, intentionally made a scratch to confirm the observation area was not moving during the test. So here I show you the video, and here I show you the hydrogen charging time. After 20 hours, the color of the polyaniline changed gradually, locally, and the number of the white area increased with time. After 50 hours, the increase in the white area almost stopped, but the whole observation area brightened slowly. So the experiment was stopped after 120 hours. This is optical image of the polyaniline. So after 20 hours, the whitening was observed locally, and the numbers of white area increased with time. After 60 hours, the increase in the white area almost stopped, and the wall observation area brightened slightly. Because the color change of the polyaniline is caused by the hydrogen, the white area indicates the high hydrogen flux area. So to analyze the color distribution of the polyaniline in detail, in the next slide, I will show you the enlarged view of the area invaded by the red rectangle. This is the polyaniline before hydrogen charging. After 16 hours, the slight whitening observed here, and whitening proceeded with time. And the white area increased, and after 53 hours, the increase of the white area almost stopped, but the wall observation area brightened slowly. This is a grain boundary map of the pure polycrystalline nickel of the same observation area. The blue and orange line shows the CSL and random grain boundaries. In this case, most of the CSL grain boundary was sigma cell grain boundaries. So by comparing the optical image and the grain boundary map, it seemed that some of the grain boundary corresponded to the white area of the polyaniline area. Then, to analyze the positional relationship between the color changed area and the grain boundaries, this optical image was finalized into these red and white images. So in this image, the red areas indicate high hydrogen flux. This is a CSL grain boundary map of the pure nickel. And this is a superimposed image of the grain boundary map and binalized image. The high hydrogen flux area does not overlap the CSL grain boundaries. So this is a random grain boundary map, and this is a superimposed image. Most of the high hydrogen flux area corresponded to the random grain boundary. So we concluded that the random grain boundaries are the preferential hydrogen diffusion path in pure nickel. In a previous research, we suggested that brightness of the polyaniline correspond to the hydrogen flux. So to check if this is applicable to this research, we calculated the brightness Y. The R, G, and the V values at each pixel in this image was extracted, and the brightness Y was calculated based on this equation. In addition, as the difference in brightness, the value obtained by the subtracting the brightness before test from the brightness at time t was defined. So in this graph, the red curve shows the time variation of the delta Y of this whole observation area during the hydrogen visualization test. And the blue curve shows the integrated hydrogen permeation current density, which was obtained by the conventional hydrogen permeation test with Devanasek cell. In this graph, the delta Y was plotted as a function of the integrated value of hydrogen permeation current density. And we could find an almost linear relationship between delta Y and integrated hydrogen permeation. So in other words, we can say by calculating the difference in brightness delta Y, the hydrogen flux distribution can be analyzed. So to analyze the time variation of delta Y at each areas, we did another image analysis. So delta Y of the area indicated by this red rectangle was extracted. So this is the area with sigma 3, this is with grain interior, and this area is random grain boundaries. Same areas are shown in the grain boundary map. So in this graph, I show you the time variation of the delta Y at each areas. At random grain boundaries, after 16 hours of the hydrogen visualization test, the delta Y increased rapidly, while the delta Y at the sigma 3 and the grain interior increased moderately. So this indicates the hydrogen flux at this random grain boundary was much greater than sigma 3 and grain interior. So we concluded that random grain boundaries are the preferential hydrogen diffusion path, and hydrogen flux at there is much greater than grain interior and sigma 3. However, in this specimen, there are a lot of CSL and random grain boundaries. So to confirm this relationship, it is kind of important to do the statistical analysis for the other grain boundaries too. Then the counter map of delta Y was calculated. So this optical image was embodied to the delta Y contour map. And by combining this delta Y image and EBSD grain boundary map, we analyze the relationship between the hydrogen flux and the grain boundary character. In this research, the grain boundary is longer than 10 micrometer was analyzed. And furthermore, we defined the hydrogen permeation time T, which is the time when the delta Y reaches to 60. So in this graph, the hydrogen permeation time T is plotted as a function of the misorientation angle of each grain boundaries. Based on this result, I can say the random grain boundaries hydrogen permeation time was shorter than sigma-3 grain boundaries. So this indicates hydrogen flux at random grain boundaries are higher than sigma-3 grain boundaries. Because the hydrogen permeation time inside grains was longer than the sigma-3 boundaries, it seems that the inside the grain shows the smallest hydrogen flux in pure network. Among the random grain boundaries, the misorientation angle with the 30 to 40 show the highest hydrogen flux. So based on Planck-Bilby formalism, the net defect density of the grain boundary depends on misorientation angle, and it becomes highest at 37 degrees. And the degree that was so calculated, the hydrogen segregation susceptibility, which is shown these purple broken lines, based on this Planck-Bilby formalism. And it's well correlated with our results. So we suggest that the geometrically large space at grain boundary is a critical factor for hydrogen flux at the grain boundaries. So these are the conclusions of this research. The hydrogen visualization system was found to have the spatial resolution of 5 micrometers. The hydrogen flux at the grain boundary was higher than that of the grain interior. And the preferential hydrogen diffusion tended to occur at random grain boundaries. The hydrogen flux at the random grain boundaries depended on the misorientation angle and was highest at the grain boundary with misorientation of 30 to 40. And hydrogen, I didn't show this presentation. So, and the details of this research is shown